Okay. Hello, everybody. So last week we started talking about conditional expectations. And what is conditional expectation? Well, it is a guess or estimate of a random variable with some partial information. So if we have a probability space with sigma algebra F, and we have a random variable x that is measurable with respect to F, and we also have some partial information, which means we have a subsigma algebra of F, let's call it G, then the conditional expectation maps X to a G measurable random variable, which we denote by conditional expectation of X given G. And this satisfies, so this X given G is G measurable and it satisfies the projection property meaning that if you have a G measurable random variable and you need to calculate the expected value of X times that, then you can replace X with its conditional expectation. For all G measurable V. In particular, you can take V as the indicator of a set in G. Then you get expected value of X times indicator A is expected value of conditional expectation times indicator A for all A in G. And these two statements are equivalent because from the second to the first, you can also pass by using linearity and also monotone convergence theorem to generalize this result for arbitrary V. And so this was the definition of conditional expectation. And on top of that, we have properties like expectations, so expectation-like properties. Namely, we have the conditional versions of monotone convergence theorem, dominated convergence theorem, monotonicity, linearity, etc., etc. And we had the special properties. So one of them was the conditional determinism. Which means we can take out what is known known means something that is measurable with respect to the sigma algebra G. Something like this, right? You have, if this is F measurable and this is G measurable, then you can take V out and you have this. And we also have Tower property. So if we have a further subsigma algebra H, so HGF, and we have X here, so we have expected value of X given H given G, or expected value of X given G given H. So they're all equal to just conditional expectation of X given H. Namely the one which contains less information. And I don't remember if we discussed this example or not, but as a consequence of this conditional determinism, for instance, if you have X and G to be independent, so if you have X and G independent, so meaning that so here we have two objects of different types, right? This is a random variable. This is a sigma algebra. So we need to explain what this means. All this means is that the sigma algebra generated by X is independent of the sigma algebra G. Okay? In other words, you just take two events from here. The probability of the intersection is the product of the individual probabilities. So if this is the case, then knowing G does not improve your conditional expectation. In other words, this is just expected value of X, which is like knowing nothing. Right? With no information. The trivial sigma algebra. And if you know everything, you simply know X because X is F measurable. Right? This we talked about last time. So any questions about the definition and basic properties of conditional expectations? This is just a review of what we did last Friday. So in most applications, this G is usually generated by some random variable or a collection of random variables. Okay? So let's look at the special case where G is generated by a random variable. Okay? Conditional expectation given a random variable. So let's say we have some random variable with values in some abstract measurable space, E. Okay. So for a positive F measurable random variable, or let's say just F measurable random variable X, we define the conditional expectation of X given Y as the conditional expectation of X given G, where G is the sigma algebra generated by Y. So just recall that this sigma Y is the sigma algebra generated by Y, which is formed of events like this, right? Y in D, D is in E. This is the sigma algebra. This collection is a sigma algebra, right? The sigma algebra generated by Y. So we simply define the conditional expectation of X given Y as the conditional expectation of X given sigma Y. In other words, we are back to the case here, right? We just take G to be sigma of Y. But this special case has some nice features. Indeed, this random variable, so note that X given Y is a sigma Y measurable random variable by the measurability property, right? G measurability. Measurable random variable. Okay? The first property of conditional expectation. So what can you say about some random variable that is sigma Y measurable? What can you say about this random variable which we know to be sigma Y measurable? Do you know a characterization of random variables that are sigma Y measurable? What does it mean to be sigma Y measurable? From an earlier chapter, right? So if you'd like to create some sigma Y measurable random variables, can you give examples of sigma Y measurable random variables? For instance, Y itself is sigma Y measurable, right? What else is sigma Y measurable? What else is sigma y measurable? Just give examples, right? Of
the sets from the sigma algebra.
So this is an event, right? And we can write it as, so indicator of y in D. We can also write it as indicator of D applied to y, right? So this is certainly sigma y measurable. Is sigma y measurable? Why is sigma y measurable? What else is sigma y measurable? Can you give some more examples? If I square y, is it also sigma y measurable? Right? Y square, y cube, sine of y. Well, whenever this makes sense, right? Whenever this makes sense, are sigma y measurable. Indeed, recall that a random variable, a numerical random variable, is sigma y measurable if and only if it's a function of y. It is a function, measurable function, of course, of y. In other words, if we have x given y is sigma y measurable, then we must have that this is a function of y for some measurable function g from the range of the values of y, which is the set E, to the numerical real line, extended real line.
Do we have any continuity assumption for the function of y?
No, just measurability. Just measurability because, for instance, this is not a continuous function, right? So we don't have continuity assumption. Okay. So that is something very nice. Something very nice. And indeed, we can also write down the projection property. So let's say we have g of y is a version of x given y. So let's say given a measurable function g, when I apply g to my random variable y, I automatically get something sigma y measurable. So the first property is automatically satisfied. All we need to make sure is the projection property. So this is a version of the conditional expectation if it satisfies the projection property. What is the projection property? Well, x times g of y is, x times v, so v is something sigma y measurable. I can replace my x with my conditional expectation, which is now g of y for all v positive, that is g measurable. To avoid complications, let me make this function positive, okay? Not here, but here. To avoid infinity minus infinity stuff, let me make this just positive. And also here, let's just say this is the case whenever well-defined. whenever well-defined. Okay, because I didn't say this is positive, so you might have cases where this is not well-defined, right? So whenever this is well-defined, we just set this equal to x given y. Okay. Anyway, so we need to satisfy the projection property for all v that is g measurable. But what is our g? G is just sigma y, right? Sigma y. In other words, my v is also sigma y measurable. So I can also write it as g of y is a version of x given y. This is even if and only if, right? If and only if. If and only if. If and only if x times, now what is v? V is sigma y measurable, so it's another function of y, right? So h applied to y is g applied to y times h applied to y. For all positive measurable function h on E. So the projection property reduces down to this property, where we use the fact that being sigma y measurable means it is just a function of y. So the conditional expectation itself is a function of y, and also the test random variables in the projection property are also functions of y. Okay? So this is the version of conditional expectation, and this is our test variable v. For instance, you can prove some useful properties, like if you have x that is f measurable, and it is independent of y, okay? So then in this case, if you look at the conditional expectation of x times some function of y given g, given y, given y, right? So this is like we know the value of h of y because we know y, okay? So we can take it out, and now we have x given y, but since x and y are independent, this doesn't really improve our estimate for x because x and y are independent. So knowing y doesn't help. You can also state it in a slightly more general framework. Let's say you have z with values in some abstract measurable space. And again, you have z and y independent. So now you can not write z here because it's not a numerical one, but you can apply a function to z, right? Some function to z. So again, you get h of y times expected value of f of z. F from h to positive measurables, measurable function. So you can check those very easily based on the definition of conditional expectation and so on. What I'd like to discuss with you is an example that is more concrete. So let's say you have a random variable. So let us assume y is a random variable with values in some set y1, y2, etc. So it is a discrete random variable, okay? Only countably many values, and assume, so, and the probability that it takes each value is strictly positive. So we do not include unnecessary values. So if it's Poisson, we just have 0, 1, 2, 3, 4, but not like -1, -2, which has probability 0. We don't include unnecessary points. We just include the atoms of the distribution. Okay? And the distribution is purely atomic. So now our G is what? So G is sigma of y. So this is simply generated by these events, right? Y is y1, y is y2, etc. The sigma algebra generated by y is just generated by those atoms, because they partition the set, right? Omega is here. So this is the event y equals y1. This is the event y equals y2. They partition omega, and they generate the sigma algebra they generate the sigma algebra of y. Okay. So last time we saw an example, namely last Friday, we discussed an example where defining conditional expectation is easy, easier than the general case, because all we can do, so in order to define x given y, x given sigma y, all we need to do is to estimate x on each of those events on the corresponding set, where this is the conditional expectation of x given the event. Remember, we defined this, right? How did we define this? Well, it is x times indicator of this set divided by the probability that y equals yi. So remember, recall, this defines x given y, x given sigma y properly. In other words, it satisfies, this definition satisfies sigma y measurability and projection property. Defines this properly, namely measurability plus projection property are satisfied. Okay. This was, I guess, one of our motivating examples, not with y, but with a structure like sigma of A1, A2, A3, etc. from last time. Okay? It's generated by countably many sets. So this example is a special case of that example. So we have A1, A2. So what we do is to estimate x on each of those events, because on each of the sets, the value of y is a constant. So here the value of y is a constant. Therefore, we can estimate x on this event with strictly positive probability using our original definition of the conditional expectation of a random variable given an event. Okay? This is not a sigma algebra, this is an event, and we define it like this. So this is our estimate on this set, We do it on each of those pieces and paste them together. Namely, we multiply those estimates by the indicators and add them up to get the full random variable, full conditional expectation as a random variable. And in this example, note that, so we have x given y, which is x given y equals yi times indicator y equals yi, right? So one thing that is for sure is that this is equal to some function of y, right? This is a function of y. Let me write it as g of y. Because conditional expectation is sigma y measurable. What is this g? What is this g? Well, when y equals yi, we have x given y. Let me write it this way. Y of omega is yi. Then this random variable takes which value? Well, only this indicator is going to give us, only one of the indicators is going to give us 1, and the rest will give us 0, because these sets are just disjoint. So if y of omega is yi, then we have this is equal to yi. Sorry, this is equal to x given y equals yi. Therefore, this is also equal to my g of yi, right? Because y of omega is just yi, so this must be g of yi. So we have g of y1, which is x given y equals y1, g of y2, which is x given y equals y2, etc., etc. And the full conditional expectation is simply g of y. This is like a summary of all those equations. So tell me the value of y, I can tell you the value of the conditional expectation. Because conditional expectation is sigma y measurable, so its value on each of those pieces must be constant. Must be constant. So why do we discuss this example? There is a good reason for this. So let's finish this example and talk about something in general. Okay? So in general, we always have that conditional expectation of x given y is a function of y for some measurable function g. So, motivated by the above example, we define the conditional expectation of x given y equals little y as g of y for all y in so this was taking values in E, I guess. So this is well defined even in cases where the probability of this event that we condition on is just 0. This makes sense even in the case that the probability of this event is 0. So we call g of y the conditional expectation of x given y equals little y. Okay? So there is conditional expectation of x given y, which is a random variable. Okay, this is conditional expectation of x given y, and this is defined in an abstract manner, right, by projection property and so on. But on the other hand, we have that this is a function of y, So whenever I know the value of y, I know the value of this conditional expectation. So when y equals little y, I know that the value of this conditional expectation is just g of y. Okay? So this g of y is just a number, right? It is not a random variable or anything, because now we are fixing the value of y. This is deterministic little y. So in this case, we say that this quantity, this number, is called the conditional expectation of x given y equals little y. Okay? So again, in more elementary settings, so okay, we define maybe probability of A given B as A intersection B divided by probability of B, but how do we define probability of B when, how do we define this conditional probability when probability of B is 0? Well, we simply don't define it. But still, we talk about things like conditional expectation of x given some Gaussian random variable is just 5, right? We still talk about conditioning on a continuous random variable whose probability is 0. Okay? And this is where it is coming from. Okay? This still makes sense because it is the value of a sigma y measurable random variable when this random variable y takes the value little y. Okay? So this way it makes sense. So when talking about conditional expectation, so there is the issue of language, because when you say conditional expectation of x given that y takes the value 5, you're talking about just a number. Okay? In other words, one realization of the random variable x given y. But when you say conditional expectation of x given y, you're really talking about this random variable, which is a function on omega, right? Its input is just omega. But somehow, with this observation, the two languages, the two vocabulary match at some point, at this point. And let me give you maybe one more exercise. So let's say we have x with values in h and y with values in e, and x and y are independent. So now, let's say we have a function of x and y, okay? So it is from h cross e to r bar plus. Maybe I should use a different letter. Let's say f. Measurable function. So now the exercise is about the following property. So you look at a function of x and y, which are independent random variables, and you condition on y. You condition on this on y. Okay? And let me write it this way. Okay? So let's try to guess this using our intuition and using maybe what we know from elementary courses. Well, we know that y is equal to little y, so I can just use this fact here, right? This just tells me that I should replace the capital Y by little y. And now this is a function of x, a random variable about x. And since x and y are independent, this should be my estimate. Because now I got rid of capital Y. So when I condition on y equals little y, this should not improve my expectation, my estimate. So this should be equal to this function. Okay? So let's call it g of y, okay? G of y. So in other words, f of x and y given y is g of y, where g of little y is defined as f of x and little y. That's a very useful property in computations. So we simply treat this y as a constant. And since x and y are independent, we simply need to calculate this expectation. For instance, if you need to calculate something like this, e to power x times y. Let's say x and y are just numerical, okay? E to negative x and y, given that y is equal to little y. Well, how do you calculate this? All you need to do is to replace this capital Y by little y, and then take expected value. In other words, this is the value of the Laplace transform of x at r equals y. We usually use this letter r, right, for this constant here, or the variable of the Laplace transform. Well, this is the value of the Laplace transform of x at the point y. So this exercise needs a little bit more work than the others because you have a function, joint function of x and y. Okay, so you need to work slightly more to get the result, but this is a very useful result when calculating conditional expectations. Any questions so far? Yes?
I actually couldn't see why we need independence of x and y to say that expectation of x given y is equal to expectation of f of x, the constant y.
Well, if you don't have independence, this means you should still use the fact that y equals little y in your estimate about x. Right? So you cannot just write it as an expectation. You actually need to know the conditional distribution of x given y to be able to calculate it. But we are not there yet, okay? We're not there yet. Okay? Any other questions? Okay, so we're following our slightly unusual path, right? Starting with conditional expectations. And today we looked at a special case where this sigma algebra, sub-sigma algebra G, is generated by a random variable. So we're done with discussing conditional expectations. Now we're going to define conditional probabilities as special cases of conditional expectations. Okay? And any guesses? How would you define a conditional probability as a conditional expectation? Can you write a probability as an expectation in general? With indicator functions. So we're going to do the same trick. Okay. Very good. So this is section 2, conditional probabilities. Okay. So again, let's say we have omega fp be a probability space. I'm going to start with conditioning on an event, okay? So let A be an event in F. So, and for each B, we define the conditional probability of B given A as the conditional expectation of indicator of B given A. This means expected value of this random variable times the indicator of A divided by probability of A. So this is, so I'm just applying the definition of conditional expectation given an event in the in last week, right? The one that we defined last week. So now what is this expected value of indicator B, indicator A? Indicator A times indicator B is what? Indicator of A intersection B. So it's the probability of A intersection B divided by probability of A. Of course, if probability of A is strictly positive. And we define probability B given A as an arbitrary number in 0, 1. Namely, we just leave it undefined, or just for definiteness, you can set it to 0 or 1 all the time as an arbitrary number in 0, 1 if probability of A is 0. So this recovers the very first definition of a conditional probability in an elementary textbook, right? A intersection B divided by A. Okay, so the more interesting one is the conditional probability given a sigma algebra. So let G be a sub-sigma algebra of F. Then for each B, we define conditional probability of B given G as conditional expectation of indicator of B, same trick, given G. And this is always well defined because indicator is a positive random variable. Okay, so we're not, we don't have a signed random variable, so we can always define it. So the mapping B maps to B given G is called the conditional probability. Conditional probability given G. Of nothing because I look at it as a mapping, as a function of B. So we need to be a little bit careful here because whenever we say we define something as a conditional expectation, we're actually talking about versions of that conditional expectation. So this just represents one version. One version, and two versions are always equal, almost surely. Almost surely. The problem here is that we do it too much. For each B in the sigma algebra, we pick one version of this conditional expectation. So I have so many sets in my sigma algebra, uncountably many sets maybe. For each of them, I pick one version. One version. So precisely speaking, for each B, we pick one version QB, let's call it QB, of indicator B given G, and QB satisfies, of course, the definition of conditional expectation, namely QB is G measurable, and QB satisfies projection property, namely, if you need to calculate the expected value of the original random variable times the indicator of a set in G, you can replace this indicator B by its conditional expectation, indicator A, for all G. And this is simply probability of A intersection B, right? So this is projection property. So all I did is to rewrite projection property with this new setting. So probability of A intersection B is the expected value of Q of B times indicator A. Okay? This is what I mean by picking one version for each B. And now, this, if I see it as a collection of G measurable random variables, so this is a collection of G measurable random variables. We can see it as a function Q of omega and B mapping to Q of B of omega. Let's call it also Q of omega and B. Okay. So what are we doing here? For each set, we have one G measurable random variable. So if I want to see it as a function of the set B as well, I have a function of two variables. One variable is omega, the second variable is B. What does it look like? You have a function of two variables. One is a point in the sample space, in the outcome space, and the other one is a set coming from a sigma algebra. Set function and a random variable at the same time. What does that mean? Kernel. So the question is it a kernel? Is it a, of course, transition probability kernel? It's going to be a probability kernel, transition probability kernel. And very unfortunate is that not always. But not always, still, yes, in good cases. Okay, so let's give a break. And in the second hour, I'll try to explain what may go wrong when you pick those versions freely without any relationship with each other, because this is what we did here. We picked each QB separately. For each B, we pick one version without thinking about other Bs. So what can go wrong when I see it as a collection of things, when I try to see it as a transition probability kernel? This is what we're going to discuss next hour.